Hello everyone. This is a final exam review session. I'm not going to formally go through the solutions, but I do have all the solutions for you. First off, there's this final exam topics and review. It's going to be in 3 parts. Part 1 is that packet on matching solids with integrals. It's posted in numerous places in Blackboard, and I sent you an email with it as well. That's 30 points. Part 2 are selected problems from exam 1 through 4, and I've got those listed here as a sample, roughly 70 points, and then part 3 is all chapter 16 problems, and we have a sample of those problems in this packet as well. As you can see, there's the part 3 problems. Now, questions 9 and 10 contain these graphs, and I'm going to send you an email with those graphs, as well as an attachment with this topic sheet, but again, it's posted in Blackboard. So there's the answers on the second page, as well as the rest of the questions for part 3. So what I did was, one thing is you could omit, and I'll mention this when I send you the email, you can omit questions 1, 2, 3, and 5. So questions 4, 6, 7, 8, 9, and 10 will definitely be on the exam, but you can omit 1, 2, 3, and 5. So what I did was I have this document posted as well without the solutions, but here is solutions to selected review questions, so all the questions except the ones I just told you to omit. And I figured Blackboard makes it hard to actually, for some reason, take photos and post them. So just look through this video, watch this video, and what I'll do though is maybe help you create a little cheat sheet of some important formulas. Like for the first exam, for the first question here, which is question 4 from part 2, let me start this over. Let me see, it's from part 2. Question number 4 is men and saddle points. The theorem, and I do have the value of D listed up here, but the formal theorem just outlined is that D is f sub x x y y minus f sub x y squared. And if D is less than 0, then it's a saddle point right away. And if D is greater than 0, then what you want to do is check f sub xx. And if x sub xx is greater than 0, then it's a relative minimum. And then the other situation is if D is greater than 0, then again you check f sub xx, and if it's less than 0, then it's a relative maximum. Okay, so that theorem you might want to consider writing on your cheat sheet. Oh, and I'll explain this in the email. You get to bring in, and I'd like you to be consistent and on your honor, treat it as a proctored final exam. For your cheat sheet, use the front and back of an 8.5 11 by sheet of paper. Okay. Okay, for this second question here, number 6 from part 2, really don't need any special formulas, so just check the solution, start and stop this video as necessary, but that should, if you pause it at that point, you can obviously see the solution to that. Similarly, question 7 is changing the limits of integration, reversing them. So you're going to have to make a sketch, and you don't really need any special formulas for that. Question number 8. This is using polar coordinates. So for this question, okay, number 8, you definitely want to know that r squared is x squared plus y squared, and that the formula for the integral is the double integral of whatever the function is times dA, which changes to the double integral of the function in terms of r and theta times r dr d theta. So so you can see the r dr d theta is your differential dA. So you might want to note that, and that should probably be sufficient for that example. And again, pause this video as needed to be able to check your solutions. For question 9 on part 1, cylindrical coordinates. Pretty much the same as the last example. You just need the r squared is x squared plus y squared again, and the r dr d theta. So for cylindrical, the formula was the triple integral of dz times r dr d theta. I'm sorry, you couldn't see me write that. And you're going to get this, you'll be given the sketch, just like I sent you the sketches here. And then we move to spherical, and the formula for spherical coordinates is the triple integral of rho squared sine of phi times d rho d theta d phi. Sorry, there it is here. So there's your formula for spherical coordinates. And there's the example. And you'll be supplied with the sketch, so you should try these on your own and check these solutions. Okay, so that's the end of the part 2 questions from old exams. And all the old exams are posted as well in but these are different problems for you to practice. But all the old exams, if you wanted to reference, are posted in Blackboard as well. This question in part 3, divergence and curl. So for part 3, divergence of a function f is partial of f with respect to x Now this is given that so let me write the formula out here. This is given that the function f is fi plus gj plus hk, and it's the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. So that's our formula for the divergence. So you can see that applied here. For the curl, you have to set up the 3×3 determinant. So if we want the formula for the curl of f, j and k, your first row, then the partials with respect to x, with respect to y, with respect to z for the second row, and then the functions f, g, and h for the third row. So there's the formula for the curl. And you can see that applied here in this example. This next question has to do with the del operator. Just remember, del is of a function is really the divergence. I mentioned that here. Del dotted with f is really the divergence of f. So it's the partial of f with respect to x plus the partial of g with respect to y plus the partial of h with respect to z. But this particular problem, problem number 2, asks you to first find f cross g and then take the dot that with del. So you could see I kind of gave you the solution literally here. So that's that one. For our line integral question, you're going to want a formula for that. And you can see I stated it here, but just to reiterate it. For the line integral, we say that the integral on the curve of a function with respect to the area, or with respect to s, excuse me, s being the arc length, recall, is equal to, and then for this question it's formally the integral from a to b of the function f of x, y, but then the differential ds is given by dx dt as a quantity squared plus dy dt as a quantity squared, and then that would be with respect to t. So we're going to want to write that formula down, obviously, on your cheat sheet. And you can see here we had to get everything in terms of t in order to be able to plug into the formula. And that worked out neatly in the end. Okay, next question is another line integral. This one really doesn't require a formula, though. You just have to get everything in terms of t. So notice how they were given x and y in terms of t. And we had to find dx and dy in terms of t and the differential dt. And then we just replaced everything to be in terms of t. So the x, the y, the dx, and the dy all replaced to be in terms of t, and then we just, from there, calculated the integral. Okay, so then when you have to calculate an integral, a line integral, when you have this vector r as your region, or curve, I should say, just remember that r is always equal to, this is number 5, r of t is always x of t times I plus y of t times j. And it would follow then that r prime of t is equal to dxi plus dyj. So that's important to remember. And the rest of it's going to be stated very similar to this, where it's telling you to calculate the work, f dot dr. So here's your function f, here's r, but again, r is, x, and x is t cubed in this case, y is t squared, so we calculated dx dt. Suppose you really didn't even need to go through this. You could have really just taken r and calculated it immediately to be 3t squared dt, but this kind of reinforces something that's important in terms of x being, or r being xi plus yj, and dr being dxi plus dyj. But you can see what we did there was we just calculated f dot dr, and then once we boiled that down, we just substituted it into our work formula. Okay, so you can check out that solution. Okay, and then we get to a problem. This is a big problem. Not a big problem like it's an issue. A big problem in terms of its point distribution. So this is number 6, and you're going to get something really similar to this. It's going to be a 5-part problem, just like this one. And this is kind of a cool problem. So first off, in part A, it's conservative if the partial of m with respect to y is equal to the partial of n with respect to x, and that's given that your vector field f is mi plus nj. So you could see we proved it was conservative that way. Okay, and then also for this situation, we have that there's some potential, what we call the potential function p, such that the opposite of del of p is equal to the function f. And this is where this implies then, since del is the derivative of this potential function, it would imply, and it has to equal f, it implies that, and I wrote that here, but just to mention it again, it implies that the potential function is the partial of this potential with respect to x times I, plus the partial of that potential with respect to y times j. So what we do is, I wrote these out with Roman numerals. You can look back at the video corresponding to this. But we basically have two main conditions. The first condition is to impose, in our search for p, to impose that dp dx, because f is equal to m and it's mi plus nj, and as well these partials, it follows that the partial p with respect to x has to equal m. And so you can see what we did there was we set that to be true. We integrated with respect to x to find p. The constant of integration could be a function of y, but then we took the derivative, the partial derivative of that p with respect to y, and imposed the second condition that must be true, that this partial with respect to y has to be equal to n. And then what happens all the time there is, well, you don't always get 0 for g prime, but when you took the partial, g of y became g prime of y. A lot of times you get a function, but then you'll have to integrate to find what g of y is. And then you take p to be the opposite of whatever that you come up with there. And then you have the potential function for, so make sure you can have enough time to pause the video and look at those two solutions if you need to. Okay, but then you have the potential function used to evaluate the integral. And the integral, the line integral of f dot dr is equal to the potential function, let's say at p sub 0, minus the potential function at p sub 1, where p sub 0 is your starting point and p sub 1 is your ending point. And so that's why we had to evaluate this integral. We used that formula, p of p sub 0, which was 0, 0, and p of p sub 1, which was 1, 2. And then you just plug those into that result, which you found for the potential function, and that evaluates the integral. And then the cool thing about this problem is that we're going to verify it. And we verify it by first, we're going to do it in two ways. First, we show that direct calculation leads us to that result. And in part D, you're going to have to calculate f dot dr. And again, dr is dxi plus dyj in general. Just take the dot product. I showed it explicitly there. And then you're going to have to get everything in terms of x and y, or sometimes you can get one integral in terms of x and another in terms of y. This one, I just got everything in terms of x. But sometimes you have to mix them, but they have to obviously match. And then we crunched that down and we were able to prove that it was actually true. But then what part E does for us, which is really cool, is it verifies that the integral is path independent. That is, we have f dot dr, we're just going to take a different path now. But now when we take these paths along these different curves, make sure you know to determine what variable's changing and the value of the one that's staying the same. So along C1, y is always 0, and dx is changing, so dy is 0. Then you can calculate that integral. And then for C2 in this case, x is always 1, and dx is not changing. dy is what's changing here as you move up. And then that would be the integral from 0 to 2 of, all we did was plugged in these dx and dy's and the x's into this f dot dr, because that's what we want to evaluate. and we were able to show that that was equal to 2 as well. So that actually shows path independence. Alright, so then we get to, I guess, the last page. And this is Green's theorem and the Divergence Theorem. So, regarding Green's theorem, again, you want to remember that R is xi plus yj, and therefore the dr is equal to dxi plus dyj. And Green's theorem, I stated it in the context of this solution up here for us. So it's right here, but just to the line integral along a closed path of f dot dr is equal to the double integral over the region of the partial of n with respect to x minus the partial of m with respect to y times the differential of area. And this is where f is equal to, again, mi plus nj. So you can see what we did there was in the solution. So that's kind of a busy solution, but we worked out the the right hand side first. Calculated the partials, literally calculated the integral. Okay, so, and then we set up for the path. And the path, the region was 0, 0 by 0, 1, so it's basically just a square. And for that left-hand side, we have to calculate f dot dr. So I showed it literally here for us. And then the same procedure as in that last example, where when you move along one of these line segments, you have to make sure you know what variable is constant and what differential is going to be 0. So you could see that along C1, y is always 0, and dy is not changing, only dx is. And then you just plug into the f dot dr formula. Here we got 0, so that the integral is going to be 0. Notice for C2, x was 1, dx was 0, because along this line segment, x is always 1. Dx is not changing, it's dy that's changing as we move out. So dx was 0. And then plugging in this formula, this term, because dx is 0, that term's gone. But then dx was 1, so we got 1 squared, or 1 minus y squared, and times the differential dy, so that was our integral. And we were moving from y equaling 0 to y equaling 1. And so we crunched that integral out. So then you could check the remainder of the solution. And then we just basically add up the circled parts, which were all the parts along the curves, little line segments, and they should match, of course, to verify Green's theorem. And then finally a question on the divergence theorem. And this one's a little bit busy too, but regarding the divergence theorem, we have the formula stated there for us. Just to reiterate it. It is the surface integral, so triple integral over the surface of the divergence of f times the differential of volume is equal to the double integral over the region of, or this is the solid, I'm sorry, this is the surface, omega of f dot n dot times the differential of area. So once again, to verify that, we're going to work on both sides. Left hand side is what we literally calculate. First you get the divergence of f, which remember is the derivative with respect to x of 2x in this case, which is 2, derivative with respect to y of 3y, which is 3, derivative with respect to z of z squared is 2z. That comes out to 5 plus 2z. It's the triple integral. 0 to 1 are each of the limits of integration, so we crunch down that integral, and that is the left-hand side. And then for the right-hand side, you have to consider the normal vectors. And so go back to the video if you need to, but I think I did a nice job on the normal vectors explaining in the lecture that we had on the divergence theorem. For example, the right side is this piece right here, and its normal vector points in the positive y direction, so that's why it's j. And then once we determine what the normal vector is, we dot that with the function, so f dot n, so here's our function, so we're doing the function dotted with just j, so that's why we just got 3y, because I dot j is 0, k dot j is 0, and j dot j is 1, so that's why we got 3y. You also have to note that y is 1 as well, so along this face of the cube, y is always 1. And so then that would just become 3, f dot n would, and if we're evaluating f dot n dA, that's 3, and then the differential of area is the other two variables, in this case z and x. And then there's no need for a formal integration calculation. This is a rectangular region, so it's just 3 times, take the difference of those limits of integration. 3 times 1 times 1 is 3. And obviously you do that for the rest of them, and then you add them all up, and you verify that they're equal. Okay, so hopefully that's good as a review. If you have any other questions or concerns, don't hesitate to, email me, give me a call, and I'd be more than happy to help you with any of the other questions you might have. So hopefully you enjoyed this semester, even though it was kind of crazy. And I wish you all the very best of luck, not only on our final exam, but in all of your future academic endeavors.